The first thing I would like to say is that Fairmat is very updated in technological experimentation, and so I joined Fairmat in 2017, and we started using this the last framework for deep learning. So we started the annual curves, and then in 2017, TensorFlow 1.0 come out, and we started using it in 2018. Then we started to use it by torch 1 year, and we start using the transformer technology just 1 year after the release of Fairmat. So deep learning are main definition, and it's difficult to find one definition. So someone say that there is a method of artificial intelligence that teach computer to process data in a way inspired by the human brain. And another definition is types of machine learning that use neural networks with many layers. I prefer the second one because, in my opinion, this is the very difference in deep learning start training neural networks with many layers. And but so what essentially we do with machine learning? You probably already know. How many of you have already built neural networks? No, but start using as a user the machine learning techniques. Some okay. So the goal of machine learning is to building models that essentially represent our data. And so the training procedure is to find parameters of our model in order to fit our data. Okay. Neural networks are a particular kind of machine learning models, and essentially is composed by some atomic unit, that is the neurons. These neurons are connected to each other, and usually there is these layers, architectures, and the main point that I would like to announce here is that before 2006 was very difficult to train neural networks with many hidden layers. So in 2006, there was a kind of revolution, and we saw many researchers that studied the neural networks for many years. Finally, find a solution to train networks with many layers. And essentially, these 3 laboratories in the North America, in the same time, tried to build ideas and technology to train deep neural networks. And one of the main ideas is the pre-training of the hidden layers of the neural networks. And in this way, they solve this problem for the first time. And the idea is that you try to reproduce the input of the previous layer in the layer that is next. And in this way, you pre-train the network, and then at the end, you use a full training of the network in a with a procedure that is called fine-tuning. This procedure now is not used yet. Actually in these times, but it's very important because in the it is used now in the transformers and the natural language processing task. Another point that facilitates the start of the deep neural network was the availability of open source software that is able to train the neural networks, and also the architectures, the computational power, because the neural networks can be trained using graphical processing unit, GPU, and after 2006, manufactured of computers started to build something that is called tensor processing unit, that are processor especially focalized for the machine learning. So neural networks obtain a lot of success because they are able to model very very complex nonlinear process, but neural networks are essentially a black box because it is very difficult to know what happens inside a deep neural network. So if you ask to someone that built a model with neural networks, why this network produce this input, this output, even specific input, probably he cannot, she cannot explain why. And another things, if the model makes a mistake, can we understand why the model makes a mistake and fix? These problems are very important in some domain, and for this reason, okay, this is a slide that I like very much, that explain the black box model. So there is if someone asks details about the answer, okay, what do you do? Well, just reorder the data, put another data inside our tool, and let's see what's happening. Okay, so black box. There is some pro and some drawbacks. So we just need data. Okay. We don't need to understand the process behind it. Okay, we have high accuracy, and the neural network are very good in managing large amount of data. Okay, but at the end we have low interpretability and difficult to explain the decision, the possibility to not reproduce the exact experiments. And last but not least, the systems can reflect biases from the human world, So we have to be very careful about the data. So, for example, we have to be very careful about some medical problem, like criminal justice, medical decision, accident with self-driving vehicles. For this reason, there is a new trending topic in the neural networks world, in the deep neural networks, that is to try to explain what's happening inside the deep neural networks. Okay, this is just an overview about the future. Probably this will be very field. But then go back to Fairmat. In some financial task, you need to explain to the stakeholder why a decision or a value is so there is some financial task that we are able to try to treat with neural network, like market prediction, fraud detection, help the development of new financial products. But because of this black box nature, deep learning is not used in every financial task. Some kind of task that need explanation cannot be used, cannot be afforded with this method. But I would like to show you one of the example where we can use deep learning in some numerical tasks. So segregated funds. Segregated fund is an investment fund administered by an insurance company. And like other financial instruments are regulated by European legislation. And the Solvency II normatives that also Andrea mentioned before ask the insurance company to produce return scenarios made by 1,000 trajectories of returns of these segregated fund using some assumption and some regulation assumption and company assumption. These returns are generated by some statistical process inside with a lot of let's say rule-based assumption inside that is called asset and liability management engine, so ALM engine. We can see this statistical process lies like a black box. So the input of this process is economic factors, trajectories of economic factors, as the output is gross returns. So the output is something like this, is like 1,000 trajectories of possible returns. Okay, we can see these scenarios in a more simple way using percentiles. So we can see the mean, the percentile of 50, 10, and 90, and these show the dynamics of our scenarios. Okay. In 2018, the European legislation asked insurance company to add something about segregated funds. So instead of predict 1,000 trajectories with the Solvency II assumption, the regulator asked to produce 30,000 trajectories with new assumption described by the regulations. So companies quickly in 2018 had to design a new LM simulator specific for this new regulation and produce a lot of simulation. So the problem was that the insurance company to design and develop this simulator in short time, and also the other problem is that insurance company would like to not happy to produce such many trajectories because the LM simulation is very computationally expensive. So in that year, we started thinking and we proposed a solution. We create what we call a meta model using the black box methodology. So starting from the data that the insurance company already produced for the Solvency II normatives, we try to train a model that fit this data, and then we project new data using the new regression assumption. And we did this using linear connectors. In this case, so we offer to the insurance company solution very fast with low design cost and able to train and generate the trajectory in a very fast way. So what inside the black box method? So given the input and the output of the process, we collect this and we train our model using the input and the output of the Solvency II LM run. We estimate our model, and then we feed the meta model with the new input. And the new input is are the economic scenarios generated with the new regulation. So in this way, we was able to produce the 30,000 trajectories and following the regulation. This is fine if two conditions are met. The first is that model need to be able to generalize in unseen data, and this can be used can be done using methods that avoid overfitting. Do you know what is overfitting? Yes, no? Okay. Well, I show you just a slide about the fitting. Just yes. So if we have many parameters in our model, probably we adapt our model too much in our training data. So what's happened is that we are in the right figure. So we adapt our model too much to the training data. And what about if we feed our model with new data that the model has not seen in the previous in the training phase? So probably we made the wrong decision. So there are many ways to fight or overfitting. The first and easy way is to use the stopping. So because training is a therapy process, usually we have a measure of our error, and during the training procedure, is iterative. The error go down in the training set, and then we keep apart a split of our data that we use just for testing. And when the error in the testing started to increase, so this is the moment, that is the moment to stop the iteration. And this is the first and effective way to fight the overfit, to fight the overfitting. You have, of course, to be very careful to select your train testing set, make sure that is equally balanced and so on. Then there are other methodology to ensure the overfit, to ensure to avoid overfitting, but I will stop here. Okay. And the second condition that we have to verify is that the domain of the new economic scenarios, so the new input that we feed the model, is included in the training domain. Why this? Because deep neural network are very good in interpolation, but is not good to extrapolation. Because, okay, if we feed the neural network with a value very distant from what the network seeing in the training phase, we are not able to check what's happening. But we are very lucky because this is guaranteed for construction, because the scenarios that the previous regulation asks to use are less volatile with respect to the SOV2. So in this case, we are in the condition to use deep learning network in some financial task. Just to answer to the previous question of Andrea in the other presentation, when we can use this kind of task, this kind of technology in the financial task. Okay, as I said before, in some cases we have to explain what's happened in our predicted values. So the model that show there as 10 parameters, more or less. Okay. So in this case, we have knowledge of what they represent. So we can, let's say, understand the process and say how to fix if something is wrong.
Mm-hmm.
So this is the key point. We have to from technological point of view is possible, but in some context is not possible because someone asked why you have predicted this.
But do you think it could be possible, let's say, maybe not tomorrow, with XI?
Sorry?
With using XI,
okay.
Explainable artificial intelligence.
Yes. I think it's possible. In the future, it's possible. With they already started to use this, for example, in autonomous vehicles and another context. But yes, it's a new field that I'm not very expert. Okay. Okay. So. I show you just 2 experiments. So this is some data, the size that we use for this experiment. So we have dimension of 30 input economic factors. So our trajectories dimensionally is composed by 30 factors. And we project for 15 years, and we have 1,000 trajectories. So we split our data in test, training, validation, and we obtain these results of squared, 97.54 is very good, and very low mean absolute error. So in this case, and this is a graphical representation of the output. So in the calibration phase, the training phase, this is what the models predict in the test set. So this data represents just the test set. And we see that the percentile are followed in a good way. The continuous line is the real data, and the dashed line is the predicted one. And we have experimented various kind of vector for this problem, and we start with feed-forward neural vector, and so the architecture is something like this. We in the input we have the first F1 Fn of the economic factor. Then we have the delta, that is the difference of the factors with respect to the previous value. And then we have also the information about the year of the prediction. So this is the first, is the more simple architecture that you can think about this. The delta information is something that adds some information about the dynamics of the trajectory. But because we are our data are sequence, architecture that are more adapted to the sequence prediction. And these architecture are very convenient and neural networks. So in this case, okay, the recurrent neural networks are some kind of unrolling the unrolling architectures. So you can think about the unit of the recurrent neural networks, something like that is recursive and intrinsically use the time dependent information inside the architecture. And so, for example, this image show some results we obtained. So using the feed-forward neural networks, in some cases, we are not able to fit well our data. So with the coverages of the high percentiles are not very good. And instead, using the recurrent neural network, we fit the trajectory in a better way. Okay. The price you pay to use the recurrent architectures is the complexity and the training time. Talking about number of parameters, for example, this kind of network that is a variant of the recurrent neural network that is called long short-term memory that is able to capture in a better way long-term information in the sequence, in the data sequence, with three hidden layers and 40 features. We have 120,000 parameters to learn. So just to give an idea, the difference between the models that I'm going to show and the using in the deep level. So this kind of methodology is now very used by our clients, and we have also implemented a service. So the insurance company directly input the trajectories for the training, then just click a button in the train process, and then another button in the predict module, and they automatically get the results. This is just to show you that from, let's say, theory, we have built our models, our architecture, and give the possibility to the client to use and train along the model and see the results. Okay. This was the first part of the numerical regression and let's say about numbers, but the second part of this presentation is about natural language processing. Why we are interested also in natural language processing? Because you have seen that so on the presentation, regulator ask insurance company to produce documents, and these documents contain a lot of information. And so, for example, these documents are public and contains characteristics and condition of insurance product. In Fairmat, we have a product that is called OpenKit Vita, And this is a database that contains all the documents of the Italian market, of the insurance Italian market. We offer this service to the insurance company, and beside the document itself, we offer also the information that are inside the document. So we need a way. We have to find a way to extract all the structured information from PDF documents. This is not an easy task because let's see this example. For example, we are interested in understand the target market of the product. So identify if the contractor can bear losses. So, for example, the example are in Italian. Sorry. In some documents, should be this sentence, quasi sostenere eventuali perdite, but also another document can have this kind of sentence, la capacità di sostenere eventualità. So, similar concept can be expressed in different ways, but we need to understand what is the target market of this product. So, the first possibility that the first solution that one can think is to identify the common patterns. So, for example, there are letters shared between these two sentences, so we can write the regular expression and filter the sentence that contain this sentence. But this is, of course, very laborious if you have to do for a lot of sentences, a lot of variables, and then what about if there is a negation inside the sentence? Your regular expression doesn't work in the way we would like, because we get the exact opposite of what we like to get. And another example of why regular expression is very difficult to maintain. What if you like to get this information also in another language? You have to rewrite completely this regular expression. So, but we are lucky also in this case. There is a natural language processing tools that can help. So, in the past, the natural language processing field produce a lot of tools that help to understand the natural language. So, for example, there are speech tagging task that is tools that try to classify the words like verb, adjectives, preposition, and dependency graphs that find relation between the word. And these tools until 2017 was developed with different technology, either Markov model, support vector machine, and also deep neural network. But in 2017 happened something. I will arrive in the next slide. But first of all, let's introduce you the concept of word embeddings. Someone know already this concept? Okay. So, Word embeddings is the numerical vector representation of a word. So we can think that single word can be represented as a vector of dimension 300, for example. And this representation project the word in a multidimensional space, and the space are to be some characteristics. The first characteristic that is similar word should be near in the space, and also the relationship between words follow the same direction. So, for example, the direction that starts from queen to king is the same direction that starts from woman to cat. Why we are sorry for this slide, but I get this slide from a very nice tutorial, but we like to remind by myself, but I hadn't so much time to present to build this presentation. Okay, but this slide is very important. So the concept is why we support them. First, because computational algorithms use numbers. So also word should be represented like number. And the second concept is that if we have a neural network that do some task, if I feed the neural network with the sentence I sat on the couch, I expect that the output of our process will be similar to I sat on the sofa. And this should be possible if couch and sofa are very near in the n-dimensional space. So in 2013, Google released Word2Vect. That is the first result of engineering of the word embedding. And this example is very nice. So if in the word embedding space, we try to subtract man to king, then at the woman, the most near word is queen. So this is very nice. Okay. So we have seen that to predict sequence, one of the better architecture is recurrent neural networks, and sequence of word is like a sequence. But this architecture has some limitation. So there is this gradient vanish problem. The memory, so the possibility to look to the previous word is not the previous words is not so long. So you can get information from the 2, 3, 5 word precedent to our word, but not you cannot to go the beginning of the sentence, for example. And then finally, these kind of networks are slow. So what is the idea that comes out in 2016 is to use the idea of attention. So instead of use a recurrent neural network, we can try to weight the most important words that are in the sentence, and weight this feature in a relative way according to the importance. And how can you can do that in the word space, in the dimensional space of word embedding? You can just do the dot product between the words. And in 2017, this paper was a very important paper that changed the world, and it's called Transformers Attentioning. So you need, and essentially say that instead of using recurrent neural network, you can use the attention to learn the most important part in the sequence. And you can learn this using neural networks, and you can use multiple attention ends to encode multiple relationships between the words. So in this way, this kind of idea facilitated the long-range dependency, so we can get the information at the beginning of the sentence, and there is not recurrence anymore. And so this is very good for training in parallel way. Then in 2019, Google released that was the first large language model, and they obtained very good performance on a lot of natural language processing tasks. And the big breakthrough was the idea of cluster learning. So BERT was a very large neural network, but not very costly. But to train need a lot of computational power. And to train this kind of model, you can use all the text you can feed into the model. So, for example, the first experiment was trained using all Wikipedia data, and they trained for 4 days on 16 tensor processing units. But the key idea is that this model can then fine-tune it in a specific task using less computational power. So this is the same idea of the first successful experiment of training the deep neural network. So first pre-training and then fine-tuning. And so this start a lot of improvement in technology. I think everyone knows what is ChatGPT. And just to have some idea about parameters. So 10 parameters for financial models, and for recurrent neural networks, we was to 100,000. Now we are talking about million of parameters and also billion of parameters. So and the very nice things about large language models that now are also multilinear. So getting back to our problem. We need to extract information from text. Question answering is an LP task that is formulated like this: given a context and a question, formulated in natural language, find the answer in the text. So, first question: how much big is Garda Lake? The context contains the answer, and the answer is 317 kilometers square. So this is the task. Okay. Large language models can be fine-tuned on the specific NLP task. So we can get the large language models from Google, that is open source. You can download it, and then you can fine-tuning in your task. So to fine-tune the model, you have to have a data set. So for example, in the question answering field, there are some data set that is open source, and so you can fine-tune the large language model in this task. The data set that you find as open source are general purpose. So the model is then able to answer to general purpose question. So getting back to our problem, we are interested on the information about the creation date of the document. So this information is here. General purpose question answering model can do this. So you feed the model with the question. And notice in this case, we are using a multi-language model because the question is in English. What is the date of creation of the document? But the text is in Italian. And the model is able to get the answers. This is something that is available. You can find also in some websites model that already are fine-tuned for question answering. But okay. But what we would like to talk now is about some questions that are difficult to answer. Why? Because are too much domain specific. So in our case, we have these insurance documents that contains terminology and concept that is very connected to the insurance domain. And in this case, a model that is fine-tuned in general purpose data does not succeed in finding the answer. But we are lucky because in Fairmat we have a lot of experts in the insurance sector, and so we have decided to build our data set. So we asked to our colleagues to label documents using the question answering parameter. So giving the text, the labelers, annotators asked to answer these questions. What is the product? And they underline the answer. What is the name of the issuer, company? What is the class of risk range, and so on. So we collected this is my example. We collected we annotated more or less 1,000 documents. These are different types of documents that every kind of documents have some peculiarity. And the deep one is annotated with a lot of variables. So in the deep case, we are interested in extracting something like 60 variable. And so we can see that we can represent the document with 60 variables. And this is just to show you the improvement that we get with the fine tuning. So this domain, that is particular specific domain in the assurance field, with the original model, we get a FE1 score of 33, and with the fine tuning, we obtain a score of 98. And just to show you an example, we'd like to show you this example. So in this case, this is an example of the prediction of the fine-tuned model. And so, for example, the question is, what is the level of probability of not finding you? So the answer of the fine-tuning model is molto improbabile. And the original model was not able to get this. But just to show you the instance, the attention mechanism, the words of the level of probability of not finding you. First of all, this is the question is in English, the rest is in Italian. But then the text that reflects the probability of not finding you is influenzano la capacità di pagare quanto dovuto. So this part of sentence is related to the questions, but in this instant, molto improbable. But the model was able to get this. Okay. Another task that we have to accomplish is the classification of the answers. So, given the answer of the question the answer model, we have also to classify this. So, for example, the example of the previous example, what is the probability of not paying you? It's called the CRM variable. We would like to categorize in four class: 0, very low; 1, low; 2, high; 3, very high. So we have in some way mapped the word molto improbabile in the class 0. So this is another task that is possible to do with large language models. And so it's possible to fine-tuning large language models also in the text classification task. And the result can be also very accurate, but if we use the strict way of fine-tuning, in this way, the result is that we need to build one model for each variable. And because one of this model is some kind of is 2 GB, so this is not so we have to think about another possibilities, and also in this case, using the transformers architectures, it's possible to have something that is called zero few shot classifier. And in this way, with this technology, we can classify new data with a few samples, but the core idea is that the model is trained not using the class, but using the entanglement of two sentences. Or the entanglement of sentences is the fact if two sentences in agree or are in contrast. And in this way, you can build a classifier, multi-class classifier with different variables in one single. Also, in this case, we can fine-tune the model. So we fine-tune this model using many variables, but I show you just the results for the classification of these variables by using asset exit cost and to show if there is or not the exit cost in the insurance product. And before the fine-tuning, the model was a little bit confused because you can see in this green square there is the predicted label false, but the true label was true. So these are 34 error and 5 error of predicted label true and 2 label false. After the fine-tuning, we obtain the result. So we made just 2 errors. Okay. Finally, just give an overview about how powerful are transformers. Self-attention and transformers can be used also in vision, and the concept is the same. The weight, the attention weighting can be used in the images, and the output of the attention head can enhance some particularity of the images. For example, the first and the object that comes into our results. The second is the part of the building, and so on. And why I talk about this? Because in our task, that is extract information from documents, we have to manage also the tables. Tables, if the document is not right very in the good way, some tables are very difficult to analyze, and so to help us to extract these numbers from the tables, we have to extract this table and then understand what these numbers, how to associate these numbers to the column, the row, and so on. But the first phase is to detect the tables inside the documents. And to do this, we can use transformer with object detection. And also in this case, we can use fine-tuning. And we use that. So we have a general model that is able to detect tables, but then some insurance documents produce tables that are very different to other one, and the general purpose model doesn't work. So we fine-tune also the table detector models using our data, and also in this case we obtain a lot of improving in performance of the detection. Okay, so this is the end. I take some figures from the web, so sorry for that. That is not all from me. And I would like to thank my colleagues. And these are the references. Something like this.
Question, comments? Don't be shy. All these processes have been implemented in a laptop or
Okay. So the first part, the recurrent neural network, and the numeric part is possible to run, train also in a laptop. But the second part of my presentation, so the natural language processing part using transformer, requires a lot of computational power. So in this case, we have some GPU workstation with very good GPU, but so for example, there are some NVIDIA cards that are very good in training machine learning models, and the NVIDIA card continue to improve their usage of the memory usage and computational power. But in these days, we are like looking also to using some cloud GPU service, because we have a lot of training to do, and our infrastructure is starting to not so data for that. Okay.
yeah, indeed, I'm thinking about AWS or something like this.
Yeah, there are.
Even because at least at the beginning, these Amazon services are used to offer their space with some, let's say, economical facilities. So at least at the very beginning could be convenient to use this kind of solutions. And of course, AWS can be used scaling about according with your, let's say, with your problems, with the size of your problem. So you can ask for a certain amount of, let's say, computational facilities, or you can increase or you can decrease with a lot of freedom, let's say.
Yes. But, yes.
And you also tried to use, I mean, sort of mix between your solution and solution that can, for example, in particular, I'm thinking about LLM solution coming from tools like ChatGPT, for example, in order to take, for example, text, dividing the text in subsets, then use ChatGPT at least 4.0 to analyze these and then to recollect information and then use your method. Mixing.
Okay, yeah, it should be a nice idea, yes. We can think about this.
Because as you know better than me, you can use ChatGPT for analyzing a text. But one of the main issues is that the amount of information is rather limited. So you have to find a way to subdivide your mass of data into several steps, and then to recollect what you gained, and so on, and then repeat this procedure. Okay.
One question.
Yeah.
The second algorithm about LMP is about a plugin on some model, or is a standalone model that you modify from
So I don't
like
get the question.
plugin, something that you add from on an existing model that was, or you work based.
Okay, the fine-tuning procedure work like this. So you get the initial model, the pre-trained model from Google, let's say, and then so the model is the same model that Google give you, but then you add, let's say, the final layers. That is the layers that is responsible for the particular task, as like question answering. So to do this, okay, there are a lot of libraries, framework, open source that do that, okay, but is in some way you add a final layer in the model. We have our own code to do this, because we had to add some particular information inside the network and train the network in particular ways and so on. But you can find a tutorial about this, and using just open source framework, you can do that.
And as input, you use PDF or raw data?
Okay. This is another part of our job. So we have a pre-processing part that take the PDF, extract the text, split in sections. And by the way, we use something like similarity also to do this, word similarity. So like word embedding is, because also for extract the section of the PDF, some company write the titles in some way, others in other way. So to have something that is robust between different type of document, you have to have something that is robust, like the regular expression example that I showed you before. So then there is the module that identify the tables, as I show you, and then the tables as another algorithm to extract the information, and then the text is created like this.
So do you use some tools about explainable artificial intelligence? Because I had the chance to read something about explainable artificial intelligence, and I used to think that it was a new topic, but actually used to be new like 3 years ago. Now it's
yeah.
So
Unfortunately, I hadn't the chance of using. I know that is in development, and there are a lot of interest, but I'm not using it yet.
Okay. If there is no other answer, question. Take